A spring that can be assumed to be idle hangs from a strand as shown above. You wish to determine experimentally the spring constant K of the spring. What additional commonly available equipment would you need? What measurements would you make? How would K be determined from these measurements? B bit. Assume that the spring constant is determined to be 500 Newton per meter. A 2 kg mass is attached to the lower end of the spring and released from rest. Determine the frequency of oscillation of the mass. Suppose that the spring is now used in a spring scale that is limited to a maximum value of 25 Newton, but you would like to weigh an object of mass m that weighs more than 25 Newton. You must use commonly available equipment and the spring scale to determine the weight of the object without breaking the scale. Draw a clear diagram that shows one way that the equipment you choose could be used with the spring scale to determine the weight of the object. Explain how you would make the determination. So here, the first bit, we have to find out the spring constant or the force constant of the spring. For that, we have to use the Hooke's law. What Hooke's law states, according to Hooke's law, the restoring force is proportional to the displacement. Here, the displacement means the stretch in the spring. When you hang a mass to the spring stretches because of the force. Here, the force is the weight of the mass. Okay, so we are hanging the known mass. That mass pulls the spring downwards. So that is the displacement or the stretch in the spring. According to Hooke's law, the restoring force is the force which tries to bring the spring back to its normal position. That force is called the restoring force. So that restoring force is proportional to the stretch in the spring. Okay, so that is why F is proportional to minus x. Here, the negative sign indicates that the restoring force and the stretch are in opposite direction. That means the spring stretches downwards, and then the restoring force acts in the opposite direction. That means upward. Okay, therefore, the restoring force and the here you can say the displacement or the stretch in the spring are oppositely directed. Okay. Therefore, F is equal to minus kx, where k is the spring constant or the force constant. Here, the force is the weight of the object, that is Fg, or F is equal to mg. Therefore, mg is equal to minus kx. Therefore, k is equal to mg by x. Here, mass is known mass, and then g is the acceleration due to gravity, and I have to measure only the stretch. That stretch can be measured using the ruler. Okay, meter scale or the ruler. Using that one, I will attach that ruler to the strand, and then I will measure the stretch. Okay, that is what he is asking about. Determine the how would K be determined from these measurements? Okay, so these are the only measurement. I need the only one measurement, that is the stretch in the spring. With that, I can measure the spring constant. To measure the stretch, I need only the ruler, okay, or meter scale. That's enough for me. That is the thing. Next, he is asking us to find out the frequency. So here, when we pull the mass pulls the object down, the gravity pulls the object downwards. Because of that, the spring is getting stretched. Okay, so the spring, when we pull the spring and then leave, the spring mass system makes oscillations. That means this acts as a simple harmonic oscillator. The oscillations are simple harmonic in nature. How these oscillations are simple harmonic, we will see here now. According to Newton's second law, F is equal to ma. Am I right? So here, F is equal to mg, or F is equal to minus kx. Here, am I right? Here you see this one. These are all the force equations. Okay, the first one is restoring force is equal to kx, spring constant times the stretch. Another one is F is equal to ma. I use these two equations and then find out the condition. Okay, write the condition for the simple harmonic oscillator. As the left hand sides are same, I can equate the right hand sides. Therefore, MA is equal to minus KX, or A is equal to minus K by MX, or K by M is equal to omega square, another constant. Therefore, omega is equal to square root of K by M. So this is the condition for the simple harmonic motion. What is the condition? The acceleration should be proportional to displacement. A is the acceleration and X is the displacement. Here, the spring mass system is making oscillations. These oscillations should be simple harmonic in nature. Okay, how we can say that the oscillations are simple harmonic? When the acceleration is proportional to the displacement and the acceleration and displacement are oppositely directed, then we call the oscillations are simple harmonic in nature. Therefore, here A is equal to minus K by M times X. Therefore, the condition is satisfied. Therefore, the oscillations are simple harmonic in nature. Now we have to find out the frequency of the simple harmonic oscillator. This is called a simple harmonic oscillator. Thus, now the spring mass system is called the simple harmonic oscillator, and we have to find out the frequency of the simple harmonic oscillator. We know angular frequency omega is equal to 2 pi f, where f is the frequency, omega is the angular frequency. Therefore, frequency f is equal to omega by 2 pi. And just now we wrote omega is equal to square root of K by M. I plug in this value here. Therefore, f is equal to 1 by 2 pi square root of K by M. Instead of omega, I am writing square root of K by M. And in the question, he gave K is equal to 500 Newton per meter and then M is equal to 2 kg. From this, I will find out the frequency of the simple harmonic oscillator as 2.5 Hz. With this, the first bit is over. Now, second bit. In the second bit, what he is saying is the same spring is used in the spring balance with a limitation. That means the spring scale can measure up to 25 newtons only, not more than that. But you are given an object whose weight is not known to you, but which is more than the 25 newtons, but you have to measure the weight of the object with this only, with the same spring scale. You are not supposed to use another spring scale, but if you use the same spring scale, the spring scale will break because it is beyond the limit. The spring scale has a limit of measuring 25 newtons only, but the object weight is more than 25 newtons. So how to measure the weight of the object without breaking the spring scale? With the available equipment in the laboratory. For this, I go for the condition of the static equilibrium. Use the principle of torque. Okay. First, I will explain the static equilibrium and then the condition for the static equilibrium. Then I will explain this one. So what are the condition for static equilibrium? Sum of the torques must be equal to 0. Am I right? First one is sum of the forces must be equal to 0. And then next one is sum of the torques must be equal to 0. So what is torque here? The torque is torque or moment of a force. Both are one and same. Okay. Either we call it as torque or moment of a force. Moment of a force. Both are one and same. Moment of a force is equal to force times distance. F cross R bar. Torque tau is equal to F cross R bar. Okay. F is the force and then R bar is the distance from the axis of rotation. Just I explain that one with the seesaw. This is our common experience. Okay. We see seesaw everywhere in any park or children's play area, you will find the seesaw. Here in the seesaw, two children will sit and then one will rotate the seesaw in clockwise direction. The other will rotate the seesaw in the counterclockwise direction. Am I right? This is nothing but the torque. Okay. When the seesaw will be balanced, when both the torques must be equal to 0 or this counterclockwise torque must be equal to the clockwise torque. Understood? The torque is nothing but the rotating effect of the force. Here the child is rotating the seesaw in the clockwise direction. This child is rotating the seesaw in the counterclockwise direction. If these two torques, this is counterclockwise torque is equal to the clockwise torque, then the seesaw is balanced. That means both the children will be sitting like this. Okay. This is the condition for the equilibrium. This is called a static equilibrium. This is the condition for the static equilibrium. So same thing we will use here. Here what I do, I will hang the, so I will take a rod, ruler or the meter scale or anything. And then for that I will hang one side the, first I will hang the ruler or the meter scale to the fixed support, rigid support. And then one side I will hang the spring scale and then the known mass. Here I am taking the 2 kg only because I have already supplied the 2 kg mass. Therefore, and moreover, the 2 kg means it is 20 newtons only. Okay, not more than that. So it is within the limits. I keep that, hang that mass to the spring scale and then I hang the entire system one side. And then this is the fulcrum. Fulcrum is this is the point where the ruler is hanging from the rigid support. And then on the other side, I will keep the object whose mass is greater than 25 newtons. Okay. And what I do is now I will adjust the distances of these two. From this is the fulcrum. Fulcrum is the point where the rod is hanging, rod or meter scale or the ruler, whatever it may be, is hanging. Here I will adjust the length this side, and then this side also I will adjust so that the rod will be in equilibrium, perfectly balanced. Okay. Then when the condition is met, then I will note down the readings. Here I know the mass and I will measure the distance d2. This is F2. Here the whatever the force is acting downwards, this is F2. Okay. And here the weight is acting downwards. This is F1. Okay, and then this length is d1. That means distance between the object and the fulcrum is d1. And then the distance between the spring scale and the fulcrum is d2. And then I know F2. And then now I measure d1 and d2. Write the condition F1 d1 is equal to F2 d2. And then F1 is equal to, F1 is the unknown weight. So F1 is equal to F2 d2 by d1. And then the measured values I will substitute and then find out the force. That means the weight of the object. Here I am taking the 2 kg mass and then I am taking G is equal to 10 Newton per kilogram. Therefore, F2 is equal to 20 Newtons and then D2 is equal to 1 meter and then D1 is equal to 0.5 meters. And then I substitute the values so that I will find out F1 is equal to 40 Newtons, which is more than the um, uh, spring scale's measurable weight. Okay. So this is an example. Like this, you can do you can find out the unknown weight of the object. Okay. And then there is another method you can use. That is entire method I wrote for you. Okay. You see here, this is the one. And you can zoom it and then you can pause, zoom, and then read. You will understand. Otherwise, now I explained, that is sufficient for you. This one. This is the steps to measure the unknown weight of the object whose weight is greater than the measurable weight of the spring scale. So this is the one using the principle of levers, or I can say that static equilibrium or the torque, whatever it may be. That one you can do. This is within your syllabus. Okay, that one. And then the next one. Next one is Archimedes principle, using the Archimedes principle. Okay. So what is the Archimedes principle? You know Archimedes principle. According to Archimedes principle, when an object is partially or fully submerged in a liquid, it experiences an upthrust which is equal to the weight of the liquid displaced by the object, submerged object. Okay. So for that, what I do is I take a stand and then a table. On a table, I will keep the water jar, and then I hang the spring scale to the rigid stand, and then to the spring scale I will put the unknown mass whose weight is to be measured. And then entire system I will this mass is to be immersed in the liquid. Here what I do is I will take the water because the object will not react with the water and it will not dissolve in water. That is why I am taking the water which is available in the laboratory, And then this jar, measuring jar, and this is another jar, measuring jar, graduated jar, and then this is a jar, water jar. Okay, and I will keep the water in it, and then I will leave the object into the, I will make sure that the object will fully submerge in the water. Okay, and then what, one more precaution I will take, the object should not touch the uh, edges of the can or the sides of the can. Okay, and it will be hanging, or it will be submerged, fully submerged in the water. Now I will note down the weight of the object in fluid, that means in water. This is the apparent weight of the object, which is less than the actual weight. Okay, if I weigh the object in the air, its weight will be something. But if I weigh the object in the water, its weight will be less than the original weight. So this is the apparent weight of the object that I will note down in the observation notebook. And then when I keep the system like this, some water will overflow through the um, exit. Okay, that water I will collect in a graduated jar, and then I will weigh this water again with the spring scale, because he is a time and again he is asking us to use the spring scale. So I know this will weigh only up to 25 newtons. So therefore, I will weigh this water in batches, two times or three times, so that the spring scale will not spoil. Okay. Now, according to the Archimedes principle, what is happening here? The weight is acting downwards. The weight of the object is acting downwards in the water. And then the upthrust, the water is pushing the object upwards. So the upthrust, some water is displaced. Because of this upthrust, the water is displaced. Am I right? So the weight of this water, displaced water, is equal to the upthrust. Okay, so the total forces we can find out now. So the actual weight of the object is equal to apparent weight of the object plus the weight of the water displaced by the object. Remember, according to Archimedes' principle, when an object is partially or fully submerged in a liquid, it experiences an upthrust which is equal to the weight of the liquid displaced by the submerged object. So here, when we, this is the experimental setup. Okay, you are seeing, no? After making the experimental setup, I am measuring the apparent weight of the object. That is something, maybe W1 or W2, whatever it may be. Suppose let it be W1. Okay, and then the some water gets displaced by the object that I will measure with the measuring can, and then later I will weigh with the spring scale. So that will be W2, weight of the water displaced by the object. If I add W1 plus W2 is equal to weight of the object in air. Weight of the object, true weight. This earlier we measured, that is 40 newtons. Maybe now also it will be 40 newtons. Okay, W1 plus W2 gives the weight of the object. This is another method to find out the weight of the unknown object without spoiling the spring scale. Understood? So these are the two methods by which you can measure that. This is a beautiful question, because multiple concept question, you have to, unless you are thorough with the Archimedes principle or the equilibrium, static equilibrium, you can't do the problem. You can't answer this question. Okay. Hope this helps. Thank you. Bye bye.